and we'll see what that looks like in just a second. Before we do that, I want to point out something. Okay, let's look at our interpolated element. So what I mean by interpolated is we're going to have elements 1 and n on the exterior, and then we're going to have some number of elements 2, 3, n minus 1, n minus 2. So if this is our datum, then we'll say this is the position of x2. This is the position of x3. This is the position of x in minus 2, and so on. So if I have an integral over some number of integrals, I can break that integral up into the total integral over the whole domain is the same thing as the integral over each subintegral, summing all the subintegrals, right? And so I'm going to write it like that. So I'm going to write my weak form like that. So I'm going to have I goes from 1 to n minus 1, right? If there are n nodes, there are n minus 1 intervals, okay? Then the integral here will be from xi to xi plus 1. And then I can move the summation, I can move it inside the integral without changing anything. So if I move it inside the integral and then I write out the terms explicitly, that's what I'm going to do next. So now I have from x1 to xn, I'm just going to say dot, dot, dot. And sorry for making you write this out one more time, but we got the integral from x1 to xn So I'm just applying the actual boundary values here, substituting in the natural boundary conditions. Where Okay, wrote all that out basically just to say that, so you have all these terms that come from evaluating the boundary conditions at the nodes, right? But, and this is like x2 minus and this is x2 plus, okay? So basically this is the x2 minus means that this term comes from, you know, the interval on the left side or the negative side of the x2 node, and this term comes from the positive side of the x2 node, okay? But these are fluxes, right? And so in virtually every case, these are going to balance, right? You're going to have continuity of flux across the node, and therefore these are going to balance and they're going to be zero, okay? Again, in the standard finite element, that's always the case. There are, or could be, cases where there's other methods called the discontinuous Galerkin method, where you can actually, you know, allow for jumps and fluxes at element boundaries. But, or nodal boundaries even. But anyway, you know, in the standard finite element method, these are always going to balance or be zero. So we don't have to worry or do anything special at those interior nodes. And the other case, which again we'll talk about next time, is if you have an external point load in the interior of the element, there could also be a case where you have to do something special, right? So if you have a flux that's applied as a boundary condition, like a source or a sink in the interior of the element, we have to distribute that in some way. We'll talk about that next time. But so then, if all of those interior nodes are 0, then finally, going back to our model problem, and this time I'll go on the interval xa to xb, because that's how I defined the original model problem, or I guess, yeah, from A to B. So there we have that. So now we are ready to make our Galerkin approximation. So we're going to let U equal U of H, which is approximated by NJ UJ. I'm going to drop the summation term, just use Einstein convention. And del U is equal to Ni. Okay? So for I equal to 1, then we have that guy, dot, dot, dot. So now I'm just writing the nth equation. So in n. Now, for the second term, notice I have, in the first equation I wrote it explicitly like this, but I have d dx in u, and if I use the product rule, right, then I have d in dx uj plus n d uj dx. But uj is a constant, right? So that second term is 0. The derivative of the constant is 0. So then basically what I get ultimately is that I just have d in j dx uj. Right? Uj is a constant. In j uj. So therefore, for the ith equation, so I wrote the first and the last. Now I'll write the ith equation. Okay? So, key thing here is notice this equation here, right? You have if I were to substitute this piece into the ith equation, then I would have nixj, right? But we already showed that that has a Kronecker delta property, right? So I can basically just substitute in the Kronecker delta there, right? And then it flips, then I can, the Kronecker delta takes the qj to a qi, right? And so then I have this, and I don't have to worry about that. Of course, this step I can only do if I have interpolating polynomial functions, right? Or interpolating, if I have shape functions that have a Kronecker delta property, which I already mentioned is not always the case, but in the standard finite element method it is, right? So now we have this. And notice also that I moved this is a constant, right? So I moved this guy out, all the way outside the integral, right? And remember, these are, basically I goes from 1 to 3 and j goes from 1 to 3, and I basically indicates the number of equations, right? So each I would be one equation, just like we wrote earlier, right? And then you have this summation on the j there, okay? But when written like this is a matrix, right? So this obviously is B Ni in J times Uj, and then if we call this thing, say Fi, then we'd have minus Fi minus Qi equal to 0, and then maybe we call this thing big Fi, and with that we can write the matrix equation. So this will be K Ij Uj equals Fi, right? Which of course has the solution in vector form. U is equal to K inverse times F.